So you've seen the experiment. Let's just see if we can work out how we actually get the value for self-inductance from that graph. So that's one of the first screenshots that you've got there. And what I'm going to do is zoom in just on the action here. It's the initial gradient that we're after. Bear in mind this is voltage and that's time. So if we do that, first thing is you draw in a tangent to the curve at the initial rise. It's that initial gradient at time t equals 0 that we're interested in. We don't care if it curves off later on, it's that initial gradient is the key thing. We're also going to need to have the supply voltage and the resistance that we had connected to it, because this is just voltage going up here. So to get the gradient, you've got a change in the y, which is the change in voltage, which SparkView has conveniently worked out as 1.699, and the time change for that, which was just a tenth of a millisecond, or 1 times 10 to the power minus 4 seconds. And we're going to use those both with Faraday's law of induction equation to get the self-inductance L in henries. First thing is to get that change in voltage converted into current. Because the voltage was measured across a 10 kilo ohm resistor in the circuit, then we can work out the current by VIR, with the change in current is the change in voltage, which is 1.699 times 10,000 ohms. So that gives us a massive 16,999 amps of change. Now that happens in a tenth of a millisecond, so let's go back to this here. So the rate of change is di by dt, so it's that change in current divided by the time, we get 1.69 amps per second. That's the di by dt in Faraday's equation. So we've got that. At time equals 0, what we're saying is that the EMF, that's 6.06 volts, is the back EMF, because there's no current flows, so whatever the power supply is, the back EMF is opposing it, meaning no electrons flow for that split second until current does start up and starts to grow there. So that's why we say E is the supply, 6.06. And the rate of change of current we've got, so it just means to change the equation to get the value for L, and it works out at 3.59, which is great because we were using what was labeled as a 3 Henry inductor, and this is probably more accurate than the value that was actually stamped on the thing. I'm able to use 3 significant figures rather than 2, because if you notice at the top here, we had the resistance as 10.0, so I've got a third significant figure of resistance, even though it was 10.0.